Welcome to part 2 of the Thermodynamics of Information. I hope you've retained some of what I talked about last time. We talked about entropy and its relationship to energy, and we talked about how we can use it to bound work production and things like that. We talked about pistons, we talked about Maxwell's demons, Szilard's engine. We talked about the benefit of information processing, how if you do information processing about your environment, it allows you to harness the order in that environment. So we see it all the time in living systems, as I discussed before. We see it in single cellular organisms responding to gradients of chemicals. We see it in complex organisms like multicellular organisms that respond to complex environments. And the basic idea there is there's some predictability in your environment, and it can be harnessed to do work. And it comes from sort of state space compression or contraction. But here we're also seeing another interesting but different, related but different property of thermodynamic systems, which is that there's this matching between environment and agent. For simple environments, you have simple agents. And for complex environments like the turbulent dynamic wind field on the surface of the ocean, you have complex agents that are needed to harness them. Now, this may seem intuitively related to Landauer's principle, which is that there's a trade-off between energy and information, but it's really sort of a fact that is on top of Landauer's bound. And we're going to see, we will build to this result over the course of this talk. Hopefully we get there in an understandable way. But I'm sorry, it looked like you had a question. No question? Okay. So returning to Maxwell's demon briefly, you have this agent that's observing his environment and has some way to feed back on the environment, and in that process is able to extract thermal energy and turn it into work energy. And if this was all that we saw happening, we would see disordered energy being turned into ordered work energy, disorder into order. That's bad. That would seem to violate the second law of thermodynamics. But fortunately, we see that there's this simultaneous cost of that information processing. When the daemon has to reset its memory to its default state, there's a cost to that. And that cost will, in general, exceed the benefit that the daemon gets from feedback and control. Now, this has often been characterized with Landauer's principle, that the work investment associated with erasure must exceed kBt log 2, the change in entropy of your memory system as it compresses state space. But this assumes that you have a finite memory. And last time I suggested, well, what if as an additional resource you have a hard drive, to which the daemon, rather than forgetting what it's measured in the past, writes the outcome of each sequential measurement. Now, in this way, the daemon could perpetually move disordered thermal energy into ordered work energy, while sending random bits to this hard drive, increasing the uncertainty in the hard drive, and thus increasing the entropy of the universe, preserving the second law. Yeah.
Doesn't it cost energy to write the bit to the hard drive then?
No, not necessarily, because it's a reversible process.
But reversible just means that you pay, if I remember my reversible stuff correctly, you just exponentially, the cost of your energy is a trade-off for how long it takes the write to complete. So all you would do is, if you decrease the cost of the write, you just take longer to actually write the bit.
Yes, but if you decrease, so we discussed this last time, the bound on the cost of an operation like that is 0 in the case where you have a symmetric memory, where the size of your memory states are equivalent, and it is true that the faster that you try to execute this operation, the more cost there is to it, and that corresponds to entropy production. But it scales as the rate of computation, and so if you do it slow enough, you can essentially zero out that cost. And there are experiments that confirm this. Beckhofer, Jun did an experiment with a controlled double well system where they were able to erase, for instance, in finite time and approach Landauer's bound. Sorry, there was a question back there.
I was just, so essentially you're taking some physical aspect of this thermal energy from the thermal reservoir and you're separating out, you're essentially breaking it into two parts. Something that has the information of the system, and then something that's still the energy that is ordered and really contains no information.
So which part is which here? I'm not quite following. So
the work would be the ordered energy.
Yes, the work is the ordered energy, yes. Oh, yes, that's an interesting way to see it. So you have this disordered heat and splitting it into the ordered energy and the pure informational component of it. Okay, I like that insight. I've never thought of it that way, but it makes sense just from a flow perspective. Is that what you're saying?
Yeah.
Yeah.
I was thinking of maybe like larger systems.
Uh-huh.
That just seems like something.
That's clever. And rather intuitive. I like it. Okay, yeah.
Sorry, so if Maxwell's demon is jiggling this gate at a certain rate to add, remove entropy from the system, then he has to be writing data to that hard drive at the same rate. Otherwise, you're not actually getting the benefit of the calculation. So you have a minimal amount of time that you've got to perform the calculation. So it doesn't look like the reversibility issue.
No, again, you're going back to the finite rate. So you can control a system very slowly and give yourself plenty of time to do it. And in that way, you do achieve the bounds, the entropic bound set by reversible.
But your control rate is going to determine how much, fiddling that Maxwell's demon might get. Maxwell's demon is decreasing entropy. He's got to be decreasing at a rate, right? So, like he's decreasing at 1 bit per second or something. So you'd have to write data to that hard drive the same exact amount in order for him to know how to jiggle that gate to continue with that entropy.
Yes, the rate of the computation the slower you do the computation, the slower you would be writing information to the reservoir. Is that the relationship?
Well, what I'm saying is, you're saying that Maxwell's demon is making a decision on when to open the gate.
Okay.
He's making that decision based on information.
So,
information till you write.
So I think you're relating more directly to. So it sounds like you have some knowledge about Maxwell's demon as it was originally posed in 1857, and that's not necessarily the form that we're describing it right now. So the rate of opening and closing this gate is not what we're considering Szilard's engine, which is much, or we considered Szilard's engine. I recommend that you look at that form of feedback and control that form of Maxwell's demon to better understand what I'm talking about. So with that said, I think hopefully we're all on the same page. And I just want to generalize this picture to an information engine, a system where you have a thermal reservoir and a work reservoir and an information reservoir, where the daemon, the engine, simultaneously processes information and manipulates energy. And so you have, flows of energy back and forth between the reservoir and the work reservoir that compensate for any sort of information processing you're doing. Now, this picture may look similar to something we've considered before, a heat engine. Now, we have three components, and the reservoir. The reservoirs have some flow of energy between them. We have a hot thermal reservoir, a cold thermal reservoir, and a work reservoir. And the constraint that entropy production is always positive tells us about the efficiency of such an engine. In a similar way, we have a thermal reservoir, a work reservoir, an information reservoir, and entropy production can essentially tell us about the efficiency of these types of engines. But how does it function? Well, to answer that question, we need to understand what an information reservoir is. So we talked about how a thermal reservoir behaves in the last class. An information reservoir has a few properties that can be elucidated by considering, say, a bit string. A bit string is an information reservoir. If every 0 and 1 have the same energy, and so every configuration of the system has the same energy, then we can look at this graph of energy versus entropy. And you see that the entropy can vary while the energy remains fixed. Now, on this same graph, we can also plot a heat reservoir. This heat reservoir is ideal in that its slope is constant and thus specifies the temperature T of that reservoir. And similarly, we can consider a colder heat reservoir whose slope is steeper, or a work reservoir, whose energy can change, but whose entropy does not change. So this is sort of the characterization of these different reservoirs on this energy entropy graph. And we see that the temperature can be, that we can think of a heat reservoir and an information reservoir as having temperature. So the information reservoir is effectively 0 temperature, and the work reservoir has effectively infinite temperature, which makes sense in the context of thinking about energy flows. So like a hot reservoir is very happy to donate energy to a cold reservoir. That heat naturally flows from hot to cold. An infinite temperature reservoir is a reservoir which is going to donate energy to anything. A work reservoir is the same thing. It will give you energy no matter what you are. You can extract energy from a work reservoir no matter what. So now we have some idea of what this information reservoir is in the context of this reservoir thermodynamics. Now, what is this bit in an information string? So here we're seeing zeros and ones. Well, these have to be physically instantiated, perhaps as a particle in a box, which is separated in 2 equal sides. In this case, the particle is stored on the 0 side, or perhaps in a double well potential, where this barrier keeps the particle in roughly in equilibrium in either the left or the right side. So in general, you want metastable systems where each configuration has equal energies. And with that in mind, we can start to think about how these information reservoirs function, how information might be passed between the information reservoir and the daemon. So it might be passed through a literal exchange of bits. So let's say this information reservoir literally passes a box with a particle in it to the daemon. So it's essentially passing a 0 to the daemon. It's like, here's a 0. And then the daemon's like, thank you for that 0. I'm going to slide the barrier over to the right, and I'm going to get some work from it. And then the daemon is going to reinsert the barrier and fix the position of the particle, fix the state of the bit. Now the bit could be on the particle could be on the left or the right, and it outputs whichever side it's on to the information reservoir. And that in turn randomizes the information reservoir. So it's taken in, say, it knew it was getting a 0. It knew it was getting something on the left, and then it randomized it and passed it back to the information reservoir. So does that sort of seem like it fits what I was saying earlier about randomizing a bit string and getting work from it? So it could do this over and over and over again and perpetually produce work.
Doesn't it have to do work to put the barrier back in?
In finite time, yes. But if it happens very slowly, it doesn't have to. Yeah. Right. Yes, good question. If the states have the same energies, we can think about this system strictly in terms of the symbols, the informational states of the system, left or right, A or B. And so now let's just look at it from a symbolic perspective. You take an input from the alphabet, y, let's say the nth one, y sub n, and using the daemon's internal state x sub n at time n tau. So that's the state of the daemon. You transform the input to an output. So the daemon used its state and the state of its input to transform to the output variable y prime of n. So that's the nth output. And also updated its own state at a new time n plus 1 tau. So the daemon state itself has updated. And it's according to a joint Markov transition matrix. So this is just a very general way to take an input and map it to an output based on some internal states that the daemon has. Very, very general probabilistic information processing. So for the rest of this talk, the way we'll represent this conditional probability is with this matrix. So it's the probability of the n plus 1th state, or the state of the daemon at time tau n plus 1, and that nth output bit given the state of the daemon at time n tau, and the nth input bit. So if we were to keep track of all the input bits in sequence and all the output bits in sequence, we could see the whole information reservoir as follows. In addition to the daemon, we could see this semi-infinite input string, and now all the outputs that the ratchet is giving. So the ratchet, or sorry, I've changed language on you already. So the ratchet is what we're calling these daemons now, is something that goes along this input string unidirectionally, processing one bit, highlighted in yellow here, one bit at a time, doing some information processing about it, and turning it into an output. And this is an exactly solvable autonomous Maxwell's daemon / information engine, which was proposed like in 2012 by Debian Mandal and Chris Jarzinski. And it's a way to harness a correlated input signal, a correlated information reservoir. So this picture allows us to start using the tools of computational mechanics. We can describe the input in terms of its Hinn-Markov model generator. So in this case, we would say maybe the input is a biased coin, which outputs a 0 with probability B and a 1 with probability 1 minus B. And that is specified, the form of that is specified by a symbol labeled transition matrix. So you have the internal states of the generator, S, with outputs Y. And then you have this joint transition matrix amongst the states of the interaction bit and the state of the ratchet. So here the states of the ratchet are A and B, and the states of the bit are 0 and 1. And these arrows specify the transitions that could be made in one step of this system. So say you start in B0, that means, so your input is 0, and the state of the ratchet is B, or the state of the daemon. And you make this random transition to A1. So the ratchet has moved to the A state, and you see you've now flipped the bit, right? And now it's part of the output. So let's see. Yeah, now it's part of the output. And then you switch to the next bit. So you've gone from this bit to that bit, and in switching, you've gone to a new state in the joint Markov transition matrix. And this gives you the form of a physical information transducer. So have you guys covered information transducers at all? No, okay. Well, then I will talk briefly about what they are. They're very similar to hidden Markov model pattern generators, output machines. They're really input-output machines that have internal states that allow you to store information both about past inputs and past outputs. So the form of the joint transition matrix tells you exactly the form of a Memoryful channel. And it's much like a hidden Markov model in that each arrow is labeled with outputs. In this case, man, that's a little bit small for you guys, huh? If you see a 0, or if you have an input of 0, conditioned on 0, you see a 0 as an output with probability 1 minus p. So I'm going to write really quickly. So you have two states. Given that you're in A, you have a probability of transitioning to B. Say if your input is a 1 with probability B. So this notation here is inspired by the idea that the probability of seeing 0 given 1 is equal to B. So hopefully that notation makes some sense. Also given that you're an A. Yeah?
It sounds basically like a probabilistic Turing machine. Is there any difference?
Yeah, it's very similar. I'd say the only way that it's different from a Turing machine is that a Turing machine does not necessarily run unidirectionally along the string. I was going to make that comparison later, so I'm glad you made it for me. Right. So we have our Memoryful channel with internal states, which are the states of the daemon, the states of the ratchet. And that determines the output. So you have the input hidden Markov model with the internal states, and then you have the transducer, the daemon, the ratchet, which has internal states A and B. And then the effective hidden Markov model for the output has hidden states, which are the joint of the hidden states of both of them. And you can calculate it directly from the composition of these two two objects. So that is the computational mechanics of these information processors. They're very general. They can do many different forms of information processing, including, if they're given enough states, universal computation. So you take an input, you apply some Memoryful process to each sequential input, and then you have an output. Right? This is the output hidden Markov model. And there are a number of comparisons I'd make. There's the Turing machine, which is a stateful device which interacts with a bit string 1 bit at a time, not necessarily unidirectionally, but it's able to do universal computation, and but it's also deterministic. And then you have physical objects, biomolecules like DNA ligase, which is processing a nucleotide sequence while in contact with a thermal environment and a work reservoir in the form of an ATP concentration. So it's a very general information processing paradigm. with that in mind, what are the thermodynamics of these transducers? How much work must we invest to execute an input-output process? In the last lecture, we were talking about the cost of transforming information variables, right? So let's talk about what are information reservoir variables, what they include. Well, there's the input string, which is a sequence of yn to infinity. There's the output string, y prime of 0 to y prime of n minus 1. And then there's the ratchet or demon state, x sub n, at time n tau. And thus, the change in free energy of the system, because this is a system where all states have the same energy, is equal to the change in the Shannon information of the joint information reservoir. So you've got, here's this ratchet state at time n, the input string state at time n, the output string at time n, and then the same for time n prime of tau. And this, in turn, bounds the work production. So the work production is bounded by a change in Shannon entropy, which you can show asymptotically is bounded by the difference in entropy rates. So this is what's known as the information processing second law. So asymptotically, the entropy rate of the input minus the entropy rate of the output bounds the amount of work that you must invest to execute an information processing protocol. And you can calculate those quantities from the computational mechanics side of this problem, from the input generator and the output generator. And so we see that information predictability order. So if the entropy rate of the input is very low, that means that you can use that input to generate work. So we see three possible types of functionality. We see the case where the work invested is negative, meaning that you're extracting work from the system, and where the entropy rate of the output is greater than the entropy rate of the input. So this is what I was describing earlier, right? Where you're taking an ordered input sequence and producing random outputs. So this is pretty much Landauer's principle, just with many bits in sequence. Similarly, you have sort of the reverse process where you're inputting work, the work is positive, and the entropy rate of the input is larger than that of the output. So you're compressing the system, you're making it more predictable. And then there's a dud, where you're inputting work to randomize the output. It's really not necessary. Like you can just let a system randomize potentially if you use the natural thermal motions of the heat bath to make that happen. So how do we calculate these works though? There are a couple different ways. And I'll cover two of them. And we'll start with a non-equilibrium ratchet example. So where you're not, this is something that could be executed in finite time. Let's look at this same ratchet again, this two-state ratchet, and consider a process where initially the transitions between it are thermally activated. So that means that there's some natural behavior of this system in it. If you're in the state B0, you're naturally activated along the transitions shown here, and say you make this transition. And so it's driven by the heat bath, which means that the energy difference is proportional to the log ratio of the forward transition rate minus the reverse transition rate. Or, sorry, the log ratio of forward over reverse. And this comes from the assumption of detailed balance, essentially, that these systems are reversible if you let them behave on their own. And because that energy is coming from the heat bath, you know in turn that the heat flow is equal to this energy difference, the energy of A1 minus the energy of B0. And notice you've flipped the bit, so we've seen that happen. And then the next step, you have to move to the next bit, and you have to drive the system. So you have to drive the system to this new bit, which means you're driving to A0, which means that you have an associated work investment of A1 minus A0. And what you find from this is that you can exactly calculate the work production and the heat production, and that they turn out to be equal, and that you calculate them from the transition matrix. Now, how exactly does a system like this harness energy from an ordered input? Well, there are different types of ordered inputs, as I was describing earlier. So, as you know, there are simple systems that generate very ordered outputs, very low entropy rates. So this is a memoryless system. One memory state, output 0, 1 with probability B and 1 minus B respectively. And it turns out that a simple one-state engine with the single state A is pretty good at leveraging this input, because the input creates no temporal correlations, and the engine is insensitive to temporal correlations. So let's consider this simple but ordered input. You take all zeros as your input, and this ratchet is constructed as follows. There's some probability of the A0 state returning to itself, but also a smaller probability of it transitioning up to this higher energy state. And so what happens when you do a thermally activated transition is that you wind up in one of these two states with some probability, and then when you push to the next state, so you've randomized this bit, and when you push to the next state with some probability, you drop down from this higher energy state, and you can harness that as work. So for this engine, you extract on average 1 over E kBT work. And that's as good as you can do with this type of non-equilibrium engine. However, as I was mentioning, there are different types of order. So you have simple inputs, and then you have complex inputs. In this case, I mean complex in that the statistical complexity is non-zero. So this is the period 2 input process, alternating ones and zeros, and it has asymptotically even distribution between the states E and F. And all of its order is in the form of temporal correlations. So its marginal state entropy is 1, but its entropy rate is 0. And the memoryless ratchet, it turns out, dissipates all these temporal correlations because of modularity. So I just threw that term at you, because of modularity. The fact that operations are happening locally in a subset of the information reservoir means that there are additional costs. And this is where we start to see costs of structure. So we're doing this complex computation, but let's, for a minute, with a transducer, but let's look at a more typical picture of a complex computation. Say, adding two numbers together, A and B. So you have this 4-bit input A, 4-bit alternate input, or one number A, another number B, and then you're outputting their sum. And Landauer's principle would tell us that the work required to execute this process is equal to the change in the change in the entropy of the informational variables. But is that really the case? Because we're doing this through a sequence of simpler operations. So we have this 3-bit adder here composed with other 3-bit adders. First we do execute this operation, then this one, then this one, then this one, and that's how we get our result. And then similarly, when we look at one of these 3-bit adders, it's composed then of simpler logic gates. In this case, this is how you would construct such a system out of NAND gates, and each of those NAND gates is operated roughly independently of the others. And therefore, those on their own should have their own physics, right? Their own rules of the relationship between energy and entropy. So for this NAND gate, you have 3 variables, in 1, in 2, and out, and each of them is binary. And so the random variable Zi, which constitutes its informational state, has, a size 8 to take into account each of the 3, take into account the direct product of these 3 state spaces. And there is a local Markov channel amongst the states that specifies the dynamics of the system, and localized control tells us that the minimum work required to do this operation is equal to the change in the Shannon entropy of just the local variables. And it turns out that can be greater than or equal to the actual change in non-equilibrium free energy in the global system, which is the change in the Shannon entropy of the global variables. So I want to stop for a minute. So are people understanding the distinction between the local variables and the global variables here?
Say it.
So, yeah. So we have sort of a global system, Z, and it's composed of the interacting subsystem, Zi, and then some stationary variables, right? So in that case, there's the first NAND gate that you choose to operate, and that would be Zi, and the rest of the NAND gates would be ZS. And going back to this previous one, the necessary bound on the work production is the change in Zi, whereas the change in the available free energy, which could be used to produce work, is the change in the global variables. So you were about to ask a question?
I was trying to make an analogy.
Yeah.
So with the information engine, we have this completely stationary distribution that is the daemon or the ratchet.
Mm-hmm.
And we have this data string coming in.
Mm-hmm.
So I think of the data string coming in as like the initial, and the stationary as being the ratcheter is sort of unrelated.
So it's good that you're thinking of it in that framework. The way that the interacting and the stationary subsystems are partitioned, though, is a little bit different.
Okay.
It's the daemon and the bit it's interacting with that are the interacting subsystem, and then the rest of the tape that's sort of fixed during the interaction and not interacting with the daemon. If you remember the picture, there was the information reservoir sort of sitting separate while the daemon was interacting with the bit. early on.
Okay.
Does that make sense?
Yeah.
Okay. So, right, we have the stationary subsystem is remaining fixed over the operation of the computation, while the interacting system is undergoing this local update. And the global dynamics of this can be determined. And what we find is that there's an associated entropy production with this modular implementation of a computation. The fact that we're not taking into account the whole dynamics when we're, or the whole change in entropy when, and only interacting with the local subspace. So we, this is called the modularity dissipation, and it's equal to the work invested to do a local operation minus the global change in non-equilibrium free energy, which is really the difference between the minimum work invested in local control versus the minimum work invested by doing globally integrated control, where you have simultaneous energetic control of all components of your energy landscape. So, you know, ideally one would be able to do that, but practically that's very difficult to do. Modularity is a practical tool that we use so that we can sort of glue logical operations together to perform new and interesting functions. And what we find is that this is equal to a difference in entropies, which reduces to a mutual information, a difference in mutual informations. So you have the stationary subsystem, you have the mutual information between the stationary subsystem and the interacting subsystem initially. So that's this region, minus the mutual information between the final state of the stationary subsystem and the, or excuse me, interacting subsystem and the stationary subsystem. So it's this atom minus this atom. Now, this picture doesn't include all the atoms that you might have in theory, right? Like, we're missing something in that picture, right? We're missing the information shared between these two systems. But because you have this local control, you find that this variable is shielded from this variable. So its difference reduces to a conditional mutual information, just this wedge here. And this quantifies the dissipation associated with forgotten global correlations. So this cost tells you an additional entropy production that comes from the structure of your computation. And it's beyond Landauer's bound, in essence. It tells you the efficiency of different computational architectures. So in the context of a thermodynamic transducer, as we were talking about before, the ratchet and interaction bit are the locally changing elements. So the local bound on the work production is the change in entropy of this bit and the ratchet state. So that's just these two variables. And then the change in non-equilibrium free energy is the change in energy including all these bits, or the change in entropy including all these bits and all these bits. And plugging in to the expression for the modularity dissipation, you can kind of identify the different components. So the initial stationary state is, or excuse me, the initial interacting system is the initial state of the ratchet and the initial state of the bit. Then there's the final state of the interacting system, which is the final state of the ratchet and the final state of the bit. And then there's the stationary subsystem, which is all the rest of the string, which is held fixed over this local computation. Okay, so this quantity right here is something you can calculate for any sort of transducer to get a sense of how much work it's dissipating beyond the change in entropy rate of the system. So, but it's rather complicated. There's 6 variables there. But we can, in certain special cases, prove some interesting things. For instance, we can consider pattern extractors, where you take a temporally correlated input, like the period 2 process, with non-zero complexity and map it to a temporally uncorrelated process, which has 0 complexity. And you find that thermodynamic efficiency, which corresponds to 0 dissipation from modularity, is equivalent to the ratchet being predictive of its inputs. So what that means is that the ratchet state is a function of the input past, which contains all necessary information about the future of the inputs. This is familiar, right? So this is necessary for thermodynamic efficiency. Moreover, it implies this principle of requisite complexity. An efficient extractor must at least match the statistical complexity of its environment in order to harness all these correlations in the environment. So this is what I was talking about earlier with the single cellular organisms with simple environments and multicellular organisms harnessing more complicated dynamical environments. You need to have this internal state space in order to harness these temporal correlations that are created by highly complex inputs. So going back here, we have these complex period 2 inputs, and the memoryless ratchet dissipates all the correlations because of modularity. But we, excuse me, but we have that we find that the modularity dissipation is only minimized when the ratchet is predictive, matching the statistical complexity of the input. So this is something that guided our intuition early on in trying to design our ratchets, non-equilibrium ratchets, to harness temporally correlated inputs. So for instance, we had a simple input, simple engine, complex input, complex engine. So this engine has 3 states, A, B, and C, complex, and it turns out that its stationary state has uncertainty, which is the same as the complexity of the input. Now, just to give you a little demonstration of how it works, let's say that you're driven by this period 2 input process, and you started the B0 state, for example. First, you make a thermally activated transition, either here or here, and then you, with some probability, make this energetically favorable transition and generate some work. And then again, you make a thermally activated transition, and then you generate some more work. And oh look, you're back where you started, and you've generated some work. So you have a stationary work-producing dynamical phase. And so this is sort of this clockwise phase where you're producing on average, if delta is very small, kBt over E work, investing negative that amount. You always got to keep track of which direction work is going in the diagrams. When I write work down, just as a reminder, it's always going into the system. It's the work you do on the system. Similarly, the heat is always the heat dissipated out of the system into the thermal reservoir when I write it down. But this is not the full story, because we didn't have to start in B0. What if we started in A0? Well, if we started in A0, you're most likely to make this transition from A0 to B0, and then when you're driven to the next state, you dissipate energy. Oh, that should be kBT. And you're thermally activated again, and then you dissipate. But so now we have a work dissipating cycle as well as a work producing cycle, and it turns out that they, when you average them together, net to work dissipation. So this is kind of a problem, except that the work dissipating cycle is unstable. There's some small probability that you go to this synchronization state, C, and if you follow the dynamics of this engine for a couple steps, bam, 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 you synchronize to the work-producing dynamical phase. And so you see sort of this picture of non-ergodicity in the dynamical phases of the system. You start in the counterclockwise dynamical phase where you're dissipating heat, but with some small probability you transition to C, and then from C you transition to the clockwise phase. And so asymptotically, you approach the work-producing dynamical phase, which is good. But, so we have a non-equilibrium ratchet, which is harnessing temporal correlations, which could not have been harnessed by the memoryless ratchet, the simple ratchet. The complex ratchet does great. But it's not achieving the Landauer bound, or the IPSL, the Information Processing Second Law, which tells us that this should be greater than or equal to the change in entropy rate of the inputs and outputs. So to achieve that bound, you need to operate very slowly, quasi-statically, as I was discussing earlier with you. So for such a system, you slowly manipulate the energy levels to move between states instead of letting the separating into sort of thermally activated and then work-producing phases. So as you're making this transition, for instance, you're simultaneously dissipating heat and dissipating work, which is proportional to the log ratio of the probability of the two states. So the work and the heat are the same. And when you average over them, you find that the work and the heat wind up being equal to the change in the Shannon entropy of the initial and final variables like we wanted. So you're achieving the bounds. And then when you switch, because everything is equally energetic in this picture, there's no work or heat production. And so we can achieve the information processing second law bound if the modularity dissipation is minimized. So to see how you would do this, again, we're going back to computational mechanics. So by storing the globally relevant correlations in a ratchet, you are able to minimize the modularity dissipation. And you do this using the input epsilon machine. It gives a prescription for designing the optimal quasi-static ratchet. So say you take the golden mean input, and it has symbol labeled transition matrices given by T. Well, then you choose the the local transition matrix over the joint states of the bit and the ratchet to be you choose the transitions to be non-zero only if the transitions of the associated input are non-zero. And this actually underspecifies the ratchet, but it gives you a rough way to determine the predictive ratchet. So looking at the transducer here, you see that it's pretty much topologically the same. There's just this extra arrow here because of an unspecified transition. And that's up to your own choice. It doesn't affect the thermodynamics, adding that extra arrow. It looks like you had a question.
Why doesn't it affect the thermodynamics?
Because you never wind up in the initialized state that would take you along this transition. So the thermodynamics of that transition don't matter. So you can just you could make it go wherever, and it doesn't matter. So in this case, you're never going to wind up in the C state with an input of 1. Right, yeah, because we see that from the C state, you always output 0. Does that make sense? So obviously you could have some errors in your estimate of your input machine. And if you did, that would make every possible transition available to you. But nonetheless, this is basically the way to design the transducer. And then from the transducer, the joint Markov model over the states is exactly specified as well.
One way to simply point of perspective.
Right.
Here, you don't know what's going on in the process. You reset.
Right.
And start state.
Yeah. That is why I put that arrow there. That was a good point, because this is effectively the start state of the system. Yep. So, as it turns out, that machine is predictive and it's efficient once it stays synchronized to the states of the input. And so it minimizes the modularity dissipation because of that, because it's predicted. If it's synchronized to the states of the input, then it's necessarily a predictor. By contrast, I keep on ragging on these memoryless inefficient extractors. You know, we construct a transducer as well as its associated joint Markov transition matrix, and we find that it dissipates 0.174 kb, which is indeed the amount of temporal correlations in the input string. The temporal correlations being measured in terms of the difference between the entropy rate and the single symbol entropy. And so we see, yay, at the top, the predictive one achieves IPSL, the bottom one doesn't achieve the IPSL. Now, we talked about pattern extractors. Yeah, what's up?
Is there some sense of the one that achieves IPSL, so it's got more states with the transducer and the Markov model?
Yes.
It's got more states. And if it's physical, I can sort of enforce detailed balance on all of those conditions.
So this is not detailed balance. This is quasi-statically implemented. Yeah.
So there's no sense of the energetic cost of switching between the states of the extractor.
There's no sense of the cost of switching between energetic states of the attractor. Sorry, let me think about it. Well, there is. It's just a different cost. It isn't determined by the conditional transition probabilities. It's determined by the expected probabilities of each state at the beginning and the end of the computation. So in this case, you're rightly pointing out that some of these arrows are unidirectional, right? And if we had this system implemented with the non-equilibrium version, what you would find is that this transition dissipates infinite energy. This would correspond to an infinite negative energy change, which would be problematic, highly dissipative. But if you allow yourself slow quasi-static control, you can make these sorts of transitions at least asymptotically in long times.
Okay. So they still lost some energy? I don't know, like, from a different framework maybe, but...
Right. It's a different calculus. It's based more on the state probabilities in the quasi-static case than in the non-equilibrium case where it's based off of conditional transition probabilities. Does that make sense?
Yes.
Okay, good. All right. So we've looked at extractors, things that take structured patterns and generate IID randomness with them. What if we consider pattern generators? We consider systems that take uncorrelated inputs and try to create structure out of them. What are the constraints on their behavior? Well, we find something fairly similar. We find that efficient generators are ones which are retrodictive as opposed to predictive. They're retrodictive of their outputs, while extractors are predictive of their inputs. So you could, in theory, generate an output with a predictive epsilon machine. You could make the states functions of output pasts, as we discussed earlier. Well, earlier we were discussing input pasts, but we could do the same thing for output pasts. But unfortunately, such a system would dissipate quite a bit of energy. It would dissipate 2/3 of kBT log 2. What we would like to do instead is take the time reversal of the reverse time epsilon machine. So that's a retrodictive. So if you take the reverse time epsilon machine, it's going to be predictive of the reverse process. But then if you reverse the arrows, it will be retrodictive of the forward process. Did that make sense?
Yeah.
Okay. You've covered this before. You did mixed state machines, right? Okay, so these are useful in that they tell you efficient generators. So this retrodictive generator is a function of the future, which contains all the necessary information between past and future, right? So this time reversal of the reverse time output epsilon machine also gives us a prescription for designing optimal quasi-static ratchets. So this is our desired output process, the epsilon machine of it. The basic prescription is that you make the ratchet input agnostic. You make the ratchet input agnostic for any particular hidden Markov model. So you take a hidden Markov model and you say, this is essentially equal to my local transitions, right? So this would be this is not necessarily the epsilon machine. This is any hidden Markov model that generates the desired output. And this would be the way that you construct the hidden Markov, or excuse me, this would be the way that you construct the ratchet. And so we see for the retrodictive efficient generator, this is a transducer, which is input agnostic, which produces the desired process. And this is the associated joint Markov transition matrix. And it produces 0 entropy. And then we have the predictive inefficient generator, input agnostic, and here again we've constructed the joint Markov, process that describes the ratchet. So again, just to reiterate, the work that you're doing with the predictive process is more than the work done by the retrodictive process, the retrodictive generator, by an amount of 2/3 kBT log 2. And that's considerable. Like, per bit. That's per bit, 2/3 kBt log 2. So interestingly, you can also vary kind of continuously between these two different types of generators. So on one end you have the epsilon machine, and on the other end you have the time reversal. And this is the dissipation, the blue curve. And so it maxes out at 2/3 kb log 2 and goes down to 0. And as the unnecessary memory of past outputs decreases, you find that your dissipation also decreases. So it appears that the more unnecessary memory you store, the more inefficient you are if you're generating a process, which is interesting. It's a prescription for doing efficient modular pattern generation. So just to step back and summarize, we've seen three or four things. We've seen the IPSL governs information processing, that information is a thermodynamic fuel and that you're bounded by the entropy rates of your input and your output. And we've seen that the modularity dissipation must be minimized to make full use of that informational fuel. And then we see that for efficient pattern generators, to minimize that modularity dissipation, you must be retrodictive. And this comes from a cost to excess memory of the past. And then similarly, we've seen for efficient pattern extractors, you need to be predictive of your input. And that leads you to the cost, or the principle of requisite complexity, that you must match the complexity of your environment to harness all the correlations within.
By excess memory, you mean there's extra or you're excessive?
Extra.
Okay.
Yeah, extra. Exactly. So, right. Yeah, back to the thermodynamics of requisite complexity. I hope this gives maybe some thermodynamic basis for understanding the relationships we see in living organisms, the apparent complexity of organisms that live in complex environments and simple organisms that live in simple environments. So that's it for today. So that was my goal, to sort of hopefully prove that there's a thermodynamic basis for complexity in agents, whether they're biological or possibly constructed artificially